Welcome my friends, welcome to my next lecture. So now this lecture my plan is to talk about what is called scalar line integral. Now if you remember in my last lecture I gave the notions of what is called smooth curves, contours, oriented curves. Of course I didn't say explicitly, in I think next within a couple of minutes you will see. So if there is a time, of course. So the concept of smooth curves, contours I have discussed. So now I think I should discuss, in fact today I will talk about what is the meaning of scalar line integral, and of course next lecture I will talk about vector line integrals and their properties. So this lecture mainly I will focus on the concept of scalar line integrals, couple of examples I will do and some of the properties I will discuss. Okay. So as I said, so I think I should start with the notions of what is called scalar line integral over piecewise or smooth curve. So the notions of smooth curve and piecewise smooth curve in the n-dimensional Euclidean space I already discussed in my last lecture. So now I want to define the meaning of scalar line integral over this piecewise smooth curve in Rn. Okay. Okay. So before going to define the notions of what is called scalar line integral, one need to understand what is the meaning of partition of a curve. Okay. So what is the definition of a curve? A curve is a functions, or if I want to talk about curve in say n-dimensional Euclidean space, that means I want to talk about a continuous functions from some interval I subset of R to Rn which is continuous, and that is nothing but, one can say that function is nothing but the parameterizations of my curve. So now if I have a curve, what do I mean by partition of a curve? Now just recall, if I have a say interval a to b, what is the partitions of the interval a to b? That means I will have to take finitely many points, and this, if I take this is x naught and suppose this is x n. So that means this is a partition. That means I can divide my interval a to b into finitely many spaces. Okay. So now I want to talk about the partitions of a curve. But what is the curve first? So let C be a piecewise smooth curve in Rn. That means it is either a smooth curve or it is a combinations of smooth curve like C1, C2, Cn, such that the end point of C1 should be the beginning point of C2 and so on so forth. If you have the combinations of smooth curve, this is called piecewise smooth curve. In other words, I can at most lose the smoothness finitely many points. Okay. So let C be a piecewise smooth curve in Rn, and suppose the corresponding parameterizations of my smooth curve is Rt, where T running from the closed interval AB. Okay. So now what you will do, consider a partitions of the interval closed interval A to B. Suppose this is my A to B. First you consider the partitions of your interval closed interval A to B. That means this is nothing but the partitions. That means you will have to add finitely many points. So whose endpoint A is equal to T naught. T naught is less than T1 is less than T2 up to Tn minus 1 less than Tn, which is B. So this is a partitions. That partitions we are already familiar with in our real analysis setting, right. So now once I have the partitions of my interval closed interval A to B, then these partitions on my closed interval A to B induce a partitions which I denote it as script of P of my curve C into n many sub arcs. Okay. And what are those? C1, C2, Cn I am writing with the corresponding arc length, because since I am talking about the arc, so therefore there is a meaning of arc length. So and the corresponding arc length is delta S1 up to delta Sn respectively. So that means I want a partitions of my curve. Now curve is a map, that means it has a parameterizations. I mean it will be a continuous function from some closed interval A to B to in Rn, if I want to talk about the curve in Rn, so in particular in R2, R3. So what I am doing, I am taking a partitions in the interval of my domain of my parameterizations of the curve, and that will induce a partitions of the corresponding curve in Rn or wherever I want to talk about. So that will give a partition. So the partitions of my interval AB induce a partitions in my curve C. So and the corresponding pictorially I have of course explained, and once I have the partitions of my curve, finitely many curves say C1, C2, Cn sub arcs, that is why I am saying sub arc, and then there will be corresponding what is called arc length, and that I am denoting as delta S1, delta S2 up to delta Sn respectively. For example, I tried to explain in that pictorially. Okay. For example, this is the red one, this is the curve in say R2 I am talking about, okay. And suppose this is the corresponding interval a to b where my parameterizations, right, parameterizations, it's a map from closed interval a b subset of R to R2, that will give you a curve, and this is the corresponding picture in R2. Now, what I just said, if I take a partitions of my closed interval a to b, it will induce a partitions of my curve. How? Because you see, partitions of closed interval a to b means what? These are the points like t0, t1, t2, right? So, I am writing this is ti minus 1, this is ti, and this is a point in the ti star. This is ti minus 1, this is ti, and this is the middle point. Now, once I have a point in the closed interval a to b, what is the corresponding image? So, what is the image? So, corresponding to a, the image is p naught, okay. So, that means R of a. So, if I have the parameterization, so that means what is my p naught? P naught is nothing but R of a, which is nothing but R of t naught. What is p1? p1 is R of t1, okay. What is p2? R of t2, and go on like that. So, what is pn minus 1? This is nothing but R of tn minus 1, and what is pn, which is nothing but R of tn, which is nothing but R of b. Okay. So, therefore, if I have finitely many subpoints in my closed interval a to b, then I will have finitely many points in my curve. And what I will do, so what is my C1? So, therefore, this is my C1. So, its initial point is P naught, final point is P1. What is my C2? Initial point is P1, final point is P2. So, therefore, I can break my C into finitely many subarcs, which I denote it as C1, C2, Cn. And the corresponding arc length, that means if I talk about say C1, I am saying that the corresponding arc length of this subarc is delta S1, and for C2 this is delta S2, and for Cn this is delta Sn. Once I have that one, then I am saying that okay, so now given a partitions in closed interval a to b, it will induce a partitions in my curve, and the partitions I already said. So, this is the partition. So, I can break my curve into these finitely many subarcs, okay. So, this is the corresponding partitions, okay, and the corresponding arc length I am saying delta S1, delta S2 up to delta Sn. Now, I want to define a norm of my partitions. So, because this is a partitions of my curve, so what is my norm? Norm is the maximum, like norm, if I take the partitions of my closed interval AB, what is the norm of my partitions? Just you take the length of the subinterval xi to xi minus 1 absolute and take the supremum or maximum. So, here also same thing. So, norm of the partitions, which I denote it as norm of P of my partition, which is nothing but norm of P is nothing but maximum of delta Si. That means the what is called arc length of my subarc Ci, where I running from 1 up to n. So, this is called the what is called partitions. Now, you can easily guess if norm of the partition goes to 0, that means I am taking finer and finer partitions in my closed interval AB. That means I will have the finer and finer partitions of my curve C in finitely many subarcs, and the arc length of each of the subarcs is very small. Okay. So, that is the meaning of the partitions. So, now if I tell you in one sentence, so you have a curve, you have a parameterizations. Take a partitions in the domain of your parameterizations, it will induce a parameterization of your curve. Corresponding to that partitions, I am defining a norm of the partition, which is nothing but maximum of the corresponding. Once you have a partitions of your curves in the finally many subarcs, and you just calculate the arc length of each of the subarcs, okay, take the maximum, and that I am denoting as the norm of the partitions. Okay. So, that is the meaning of the partitions of a curve. Now, once I have the notions of partitions of a curve, then you will see next slide that now I can define the meaning of what is called scalar linear integral. Okay. Look, so scalar line integral over piecewise smooth curve, scalar line integral, not scalar linear integral, scalar line integral. Okay. So, what I have to do? So, let C be a piecewise smooth curve in Rn. Now, suppose I have a function which is scalar valued, that is very important because I want to talk about scalar line integral. Okay. So, let f be a scalar valued function whose domain of definition contains the curve C. So, I think it is all right. So, start with a curve C in Rn. Start with a function, scalar valued function, then it is taking the values in R, okay, and its domain contains my curve C. Along with that, I am assuming something extra, that f is continuous and bounded on C. So, that I want to talk about, now we can guess. Once I have the function is continuous and bounded, now I want to talk about the what is called, well, I will make a Riemann sum and I want to talk about the Riemann integral. Okay, that is the plan. So, assume that f is continuous and bounded on my curve C, and this is the picture I already explained. So, this is the corresponding partitions. Okay, take a partitions of your interval AB, which is the ith sub interval is Ti minus 1 to Ti. The corresponding sub arcs will be Pi minus 1 to Pi. Okay, so this is the association. So, Ti minus 1 moves to Pi minus 1. Ti is nothing but Pi. So, and what is Pi? So, if the parameterization is R, so you can say that Pi minus 1, which is R of Ti minus 1. Okay, and what is your Pi, which is R of Ti. Okay. Once I have this one, so this is the corresponding partitions of your curve. And now look, so if I have, so suppose again, so if I have a curve in 2-dimensional thing, so that means the corresponding picture, this is the right hand side, so that means given xy in R2, so I have a curve in R2, right. So for each comma x comma y, I will have a scalar valued function, that means it will give a value at the point x comma y. That means if I draw the picture, so it will be, that means I have to bring what is called 3-dimensional picture here. That means in the z axis, so given xy, I will have the value corresponding f of xy. Okay. So now what we have to do, just make a Riemann sum that you have done in the case of Riemann integral. So look, so what I am saying, so let this be a partitions of my curve C, that means this is the corresponding partitions. Okay. Choose a point Pi star on the sub arc Ci of C. Like in the Riemann integral, what you have to do? You just take a partitions of the interval closed interval AB and take a sub interval, say Ti minus 1 Ti or Xi minus 1 to Xi, then take any arbitrary point. Okay, inside that, right. So let it be xi I, and then you are considering the value of the functions at xi I. Same thing I will do. Instead of taking the partitions of your interval AB, now I am considering a partition of my curve. Once I have the partitions, so if I take the partitions like Pi minus 1 to Pi, I take an arbitrary point inside this subarc, and that I denote it as Pi star. And with that Pi star, since f is defined on my curve C, so in particular it is defined on my subarcs Pi minus 1 to Pi, in particular it is defined at the point Pi star. So I want to make a Riemann sum. So that's exactly I am doing. So first start with a partitions, choose a point Pi star on the subarc Ci of C, define the Riemann sum, which I denoted as S P comma F. P is the partitions, F is the given functions. What you have to do, just take the value of the functions at Pi stars times arc length of my subarc Ci. So earlier what we have, you have the partitions of the interval A to B, take a sub interval xi minus 1 to xi, take a point xi I inside that interval, then you make a Riemann sum. What is that? F of xi I times length of the interval, that means xi minus 1. Exactly I am doing the same thing. Now what I am doing here, instead of taking the partitions of the interval, and I am taking of course the partitions of the interval, but the corresponding parameterizations will give you a partitions of my curve C, and there I am taking any arbitrary point in any subarc Ci, which is the corresponding partitions, right. In that subarc Ci, I am taking arbitrary point which I denote it as Pi star, and once I have that arbitrary Pi star, I am taking that, okay, calculate the value of f at that Pi star, which is possible because f is defined or domain contains my curve 2R. So that means make a Riemann sum f of Pi star times, you have to hit it with what is called arc length of my subarc Ci, and sum it up I from 1 to n because it have n many points, right. And this is called the Riemann sum, where delta Si is the arc length of my subarc Ci. Then I am saying that, okay, the scalar line integral of f over C defined by, just take the limit of norm p goes to 0 S p comma f. So that means make a Riemann sum, take finer and finer partitions. Whenever the limit exists, then I will say that this is the notations, integration over C f ds. F is the functions, C is the curve, ds, S stands for actually somehow arc length. So with respect to arc length, I am talking about the integration. So this is called the scalar line integral of f. Okay. So now I think it's quite clear. So take a curve in Rn. Okay. So if I want to talk about the scalar line integral of some curve, okay, so take a curve C in Rn, then you will have the corresponding parameterizations, let it be capital R, which will be a mapping from some closed interval AB subset of R to Rn, the corresponding parameterizations of my curve C. Then what you have to do, take a partitions of your domain of your parameterizations, that means interval A to B, it will induce a partitions of your curve. Once I have the partitions of your curve in finally many sub arcs, then what you have to do, take an arbitrary sub arc, say let it be Ci, take any arbitrary point Pi star in that sub arc Ci, and then you have to make a Riemann sum, that means sum over I from 1 up to n, f of that If I take the subarc Ci and if the corresponding point is Pi star, then take of course you have to start with the functions from some domain subset of Rn to R, and that domain should contains my curve C. That means if I take functions whose domain contains my curve C, that means function is defined in the subarc Ci. In particular, it is defined at the point Pi star. So therefore, you consider the Riemann sum, that means sum over I from 1 up to n, that means it is the number of partitions points, the corresponding curve. Then make the Riemann sum like f of Pi star times what you have to hit, you have to hit with the corresponding arc length of my subarc Ci. Okay. Then you sum it up I from 1 to n, that is the n many points are there in your curve. And what you have to do, you have to take the limit. So this is the of course the Riemann sum, and then you have to take the limit is norm of p goes to 0. Norm of p goes to 0 means I am taking the subarc or length of the subarc is very small. So that means if I take the partitions of my interval a to b very finer and finer, then the length of the corresponding subarc very goes to 0. And if this limit exists, then I will call that the line integral of my f over the curve C. So I think definition is clear. Let me do some example, then it will be more clear. Okay. So before that, before calculating some example, couple of properties I have written in scalar line integrals. First property is that if I take the constant functions 1, that means f of p is equal to 1 for all point in C. If that is the case, so integration or scalar line integral of f over C f ds, which is nothing but f is 1, that means scalar line integral of my constant function 1 over C, and that will exactly give you the arc length of the curve C. Okay, number 1. Number 2, if I take two scalar fields, that means two functions f from Rn to R, or if I want to talk about the curve in Rn. So let f and g two scalar fields whose common domain contains the curve C, because I want to talk about the scalar line integral over C. Okay, and suppose you have two scalars a and b, then this is true like in the case of Riemann integral, that is also true. So that means integration scalar line integral of a plus bg over C. So it will actually behaves like linearity, right? So a will come outside, b will come outside, this is the constant, and it will distribute like integration scalar line integral of f over C plus scalar line integrals of g over C. So that means it behaves like linearity, and that you know in case of Riemann integration, that is also true. And the third one, that is also important. So what it says, suppose you have the curve C which is divided into two adjacent species, say C1 and C2. Suppose you have a curve C which is a piecewise smooth, and suppose C is nothing but C1 union C2, and each of them C1 and C2 are smooth, then integration or scalar line integral of f over C you can break up into two parts. What is this? First one is the scalar line integral of f over C1 plus scalar line integral of f over C2. Anyhow, one example I will have, and that one I will calculate, then you will see this for like in the what is called Riemann integration. If I want to talk about say integral over a to b, okay. So integration a to b, so like this is kind of thing, integration a to b fx dx, and if I take just a point C in between, so this is same as integration a to c fx dx plus c to b fx dx. Okay. So same thing. So this is the corresponding properties of Riemann integral. So here I will have a curve C. If it is the union of two smooth curves C1 and C2 adjacent pieces, then integration over C f ds, which is same as integration over f C1 or integration of f over C2. Okay. Now I have just give some method. So method of calculating scalar line integral. So that means if I give some kind of problems, okay, calculate this scalar line integral, how to calculate that. So there are a couple of methods, if you follow then you will be able to calculate. So look, so I have written the method for calculating scalar line integral given below. So what are the steps you have to follow? So step 1. So step 1 means what? Curve is given, that means you have to find the parameterizations, right? So first one, step 1, write a parametric equations capital R t, where t running from some closed interval a b of the given curve C. So therefore if I say that okay, calculate this scalar line integral, that means I will give you some curve. So first you will get the parameterizations of the curve, that is the first one. If its parametric equation is not given, of course, if it is not given, just I am saying that curve, this is the curve, so I am saying. So first you have to get the parameterization, that is the step 1. What is the step 2? Step 2, once I have the parameterizations, then the if you get the parameterization right, then you have to calculate what is called derivative of this map R. So, that I am saying R prime of t. So, you have first, then next you have to calculate R prime t. Of course, the curve I will give that R prime t exists, that you have to believe me. So, yes, the derivative exists, R prime t, you have to calculate what is R prime t, and then you have to calculate what is the norm. Okay, though I am writing here its mod, actually R prime t is a vector in Rn, and what is the mod of the vector in Rn? Either I will write mod or norm, it depends, like it's depending on the context, right. So, if I take an element x in R and if I take the mods, perfectly all right, and if I take a vector in R2, even if I put a mod, that means actually I am going to talk about the norm of this vector. So, you can, for your convenience, you may write this is actually norm of R prime t, because R prime t is an element in Rn. Okay, so fine. So, first you get the parameterizations, then you get R prime t, that means derivative of R at the point t, calculate norm of R prime t. Third step is that once your function f is given, right, and in the domain of your functions the curve C is sitting, right. So, therefore, you just calculate what is f composed of RT, that t goes to f composed capital RT, that you have to calculate, and finally, at the end you have to evaluate. What you have to evaluate? So, left hand side, that is nothing but the scalar line integral of f over the curve C, which is nothing but exactly equal to t running from a to b, where the parameterizations you have from a to b, then you have f of RT that you already calculated in step 3, and then you have the norm of R prime t that also you calculated in step 2, and you have to calculate just simple Riemann integration that you are already familiar with, right. So, therefore, actually to calculate the scalar line integral, you have to calculate the right hand side Riemann integrations, provided you have to find the what is the parameterizations, what is derivative of these parameterizations, what is the norm of R prime t, and what is f of R comma t. If I have all those information, then if you calculate this Riemann integration, which will give the value of your scalar line integral of your functions or scalar field f over your curve C. Okay, I think next slide I will talk about one example, it will be more clear. Look, for example, this is one example. First example, okay, take a scalar field or some functions f from R2 to R. So, these are functions from R2 to R. What kind of functions? F of xy is exactly equal to y, okay, kind of projections, okay. So, what I am saying is that let C denote the upper semicircle of radius 3 centered at the origin. Look, here I did not provide what is called the parameterizations. I just say that C is the curve which is nothing but the upper semicircle of radius 3 with center at the origin. That means, if I draw a picture, so that means this is the origin, upper semicircle, right. So, kind of, and what is this? Radius is 3. So, suppose this is my 3. So, that means I am talking about, suppose this is minus 3, something like that, okay. So, now you have to get the parameterization first. So, function is given, curve is given. Now, I am saying that okay, calculate the corresponding scalar line integral of my function shape over my curve C. So, step 1, you first get the parameterizations of your curve. Now, curve is given. What is my curve? Curve is a upper semicircle with radius 3. Okay. So, therefore, what is the parameter? What is the equation of the circle with radius 3? X square plus y square is equal to 3 square. That means, x square plus y square is equal to 9. Now, what is the parameterizations? Of course, this is the in general parameterization is RT, which is cosine t or 3 cosine t comma 3 sine t, and this time full circle it is t from 0 to 2 pi. Now, I am talking about the upper semicircle, that means t runs from 0 to pi. Okay. So, first so writing the parametric equations of C, C be parameterized as follows. Look, 3 is actually coming from the radius, and cosine t sine t, that is the corresponding parameterization of unit circle. And since I am not talking about the full circle, I am talking about only the upper semicircle. So, therefore, instead of t running from 0 to 2 pi, it should vary from 0 to pi. So, that is the first corresponding what is called parameterizations of this curve C. Okay. Then you have to calculate the first norm of R prime t. Now, once we have the R of t, then you can easily calculate the norm of R prime t. And what is it? R t is there. So, what is R prime t? First you calculate R prime t. R prime t is minus 3 sin t and 3 cosine t, right? Because each of the components are very nice functions, it is infinitely many times differentiable, therefore, in particular it is once differentiable, and you can calculate the norm of R prime t. So, this is your R prime t, norm of R prime t, which is nothing but square root of 9 cos square t plus 9 sin square t, then use the trigonometric formula, you will end up with this is actually 3, and this is true for all t 0 to pi. So, step 2 is done. So, step 1, step 2 is done. Now, what is my step 3? You have to calculate what is f of RT, right. So, look, step 3 computing f of RT. Now, f of xy is equal to y given, that is the projection kind of things. Okay. So, then f of RT, which is nothing but 3 cosine t, what is this? 3 cosine t comma 3 sin t. That means it is a y, that means only 3 sin t will be there. So, f of 3 cosine t minus 3 sin t, which is exactly equal to 3 sin t. So, that is step 3 is done, and step 4 you just use the formula. So, integration of f over c ds, which is nothing but t running from a to b, if you remember. Now, what is my parameterization? T running from 0 to pi. So, therefore, t from 0 to pi, f of r t, which I already said this is 3 sin t, and norm of r prime t I have already calculated, okay, 3. So, if I combine, so therefore, this is f of r t, this is 3 dt. So, just once I have this one, then means what, 9 will come out sin t dt, and perform the just definite integral. So, that means minus cosine t from 0 to 2 pi, and this will end up with the value 18. So, this is the formula. So, that means if I give some kind of problem that calculate the scalar line integral of my functions over this curve. So, these are the 4 steps you have to follow. First, you have to get the parameterization. Second, you have to get what is called r prime t, and then calculate the norm of r prime t. Third one is that you calculate what is f of r t, and fourth one you use the formula integration c f ds, which is nothing but a to b, where the parameterization t running from a to b, f of r t times norm of r prime t dt. Couple of notes, is a very important note I have written. So, first of all, in the line integral, integration c f ds, the integrand. So, this is my integrand, right? This is the integrand. Integrand f is scalar valued functions. So, that means it is taking values in r, scalar valued function, and hence this integral is called a scalar line integral. Okay. So, my function is actually scalar field, that means it is taking values in r. So, therefore, the corresponding integral is called scalar line integral. Now, you can say that, okay, instead of taking values in r, if it takes values in r2 or r3 or rn, that means if it takes values vector value, then I will talk about, this is called vector line integral. When I will talk about vector line integral, then it is a similar kind of things will be there, but this time your function is taking not the scalar value, but the vector value. Okay, this is the number 1. What is the number 2? The value of this line integral is always a scalar, of course, because if you just look at the formula, the way I have, so this is the give you always a scalar element in R. Okay. So, therefore, this value of this line integral integration c f ds, it always is scalar. Also, you can see that the way I have defined the Riemann sum, and the norm of the partition goes to 0. What is my Riemann sum? Riemann sum is take a partitions of my curve, take any point pi star in the subarc ci, calculate f of pi star. F of pi star is a scalar because f is a scalar valued function. Then what? Then length of the subarc, that is also a scalar. So, if I take sum I from 1 up to n, this is also a scalar. If I take the norm of the partition goes to 0, so limit also be a scalar. So, therefore, the scalar line integral it always gives a scalar. What is the third one? Third one is very nice. It says that it is important to note that the orientations or directions of the curve C does not affect the value of the scalar line integral. So, you may say that, okay, so I have a curve C, for example, the last one, this one. So, the parameterizations I am taking, it is actually what? So, if I take this parameterization t from 0 to 2 pi, that means I am moving starting from 3, and then I am going in this direction and end it minus 3. Now, instead of that, if you say that, okay, I am not interested, I want to start from minus 3 and end 0, that means I want to go in these directions. Now, in that case, if I change my directions of my curve C, will it changes the value of the line integral? Answer is no. Answer is no. So, that is exactly the point. So, it is important to note that the orientations or directions of the curve C does not affect the value of the scalar line integral. That is, the integral of f over the curve C and the integral of f over the opposite curve. What is the meaning of opposite curve? If I have a curve C, opposite curve C means that means I will trace out the same set of points, but the direction will change. Okay. So, that is exactly I have written. So, over the opposite curve minus C, which traces the same set of points traced by C. So, whatever points traced by my curve C minus C, it is again a curve which traces the same set of points, but in the reverse directions. So, if I take C, minus C is nothing but the same curve, that means the whatever points my curve C traced out, same set of points minus C will traced out, but in this case what will happen for minus C, directions will reverse, that means in the opposite directions. But it does not matter, even if I take the opposite directions, the value of the what is called scalar line integral will be same. So, for example, if I take like the simple, I am just taking a circle. So, if I take a parameterization t from 0 to 2 pi, okay. So, therefore, this is my curve C. See, if I go in this direction, so starting from here, coming here, and the whatever value I will get, If I go for the reverse direction, same value I will get. Okay. In fact, if I have a parameterizations, I think if I write it clearly, for example, in a 2 dimension. So, suppose I have a curve C and suppose I have a parameterizations RT, which is nothing but say xt plus xt comma yt, okay, let it be, and say t running from say a lesser equal to t lesser equal to b. Suppose this is my parameterizations of my curve C in R2. So, what is the parameterizations of minus C? So, minus C you just check out, you just check in your home that minus C has a parameterizations. So, that means I will write this is R of say R twiddle of t, which is nothing but x of minus t comma y of minus t, okay, correct. This time t runs from minus b lesser equal to t lesser equal to minus a, correct. So, for example, so what is this? If I take t is equal to a, that means the curve C starts from the point what? X a y a, right. This will for t is equal to a, I will have x a y a, and where it will end? X b y b. I mean it will start from here and it will move here, right. So, that is the parameterizations of C. And what is the parameterizations of minus C? I have written that R twiddle of t, which is nothing but this one. Now, if C moves from the point x a comma y a to x b to y b, it is expected the opposite of the curve should start from x b y b and end at x a y a. Now, look, if I put t is equal to minus b here, that means what is R twiddle of minus b, which is nothing but x b comma y b, right. That means it starts from here, right, x b to y b, and where it will end? R twiddle of minus a. So, that is the parameterizations. What is the value of minus a? That means it is x a comma y a. That means it will starts from here, it will end here. So, that means it is the opposite directions. So, if C has a parameterizations like this one, okay, then the minus C will have the corresponding parameterization this one. So, it says that the third one, it says that the scalar line integral it is independent of its directions, okay, that is or orientations. So, whatever orientation you can take, it will give you the same value. Okay, so couple of formulas I have written. So, for line integral, so okay, so suppose if I have a curve in 2 dimension, or I say that is a plane curve. So, for the plane curve gamma, that is the parameterizations, okay, here I have written small r t, does not matter. So, since I am talking about plane curve, that means it will have only 2 components x t comma y t, t runs from a to b. Then what is the corresponding or what is called scalar line integral of f over this gamma? So, this is the formula integration a to b, this is the t varies from a to b, then f of r t, which is nothing but f of x t y t, and then you have to take the derivative of r prime t and take the norm. If I take the r prime t, what is r prime t? R prime t is nothing but x prime t comma y prime t, okay, and what is the norm? That means square root of x prime t square plus y prime t square dt. So, this is the corresponding formula for scalar line integral in plane curve gamma. So, for example, I have just put an example. So, for example, I just evaluate this line integral, a scalar line integral 2 plus x square y over the curve gamma ds, where gamma is the upper half circle x square plus y square is equal to 1. Now, upper half circle means what? That means t running from 0 to pi, not 0 to 2 pi, okay. And what is the corresponding parameterizations? So, it is the upper half circle, that means it is a unit radius, that means this parameterization is very nice. So, your parameterization is cosine t comma sin t, t running from 0 to pi. So, that is the corresponding parameterizations. Get the r prime t, what is this? Minus sin t comma cosine t, right. Then you have to calculate this one. So, this is nothing but 0 to pi, this use the formula f of x t comma y t, this is your f functions. So, that means it should be 2 plus cos square t plus sin square t, because this is the corresponding parameterizations, and then you have square root of x prime t square plus y prime t square, but that means what is r prime t? Minus sin t plus cosine t. So, therefore, what is the square root of norm of r prime t? If you calculate norm of r prime t, which is nothing but sin square t plus cosine square t, and which is 1, right. So, that means it will not contribute anything, it is 1, it is end up with 1 here, then dt. So, that means it is very simple integral 2 plus cos square t plus sin t dt, and if you calculate it, first one will give you 2 pi and second one will give you 2 by 3. What you have to do? You have to just use the formula or substitute it, okay. So, that means if I take cos t is equal to say x, so then you just use the substitution formula, right. So, cos t is equal to x or x twiddle, that means minus sin t dt is equal to dx twiddle, and then corresponding integral will change and this will give you the value 2 by 3, okay. It is okay, very simple. So, I did not complete it, you just complete it. So, if you do that integration, so it will have 2 pi plus 2 by 3. So, that is the formula. So, this is the formula for the plane curve gamma, and if I want to talk about what is called scalar line integral. Okay. Another one, this is very nice. So, let us say that, okay. So, this example is very nice. So, this time actually I am in the figure I am saying that consider the curve C, which is C1 union C2. What is my C1? This is my C1 and this is my C2. C2 is nothing but the line segment joining the point 1 1 to 1 2. And what is C1? C1 is actually the parabola. I have written C is the parabola y is equal to x square. Starting point is 0 0 and end point is 1 1. Okay. So, therefore, I have the curve C is equal to C1 union C2, and I say that, okay, calculate this integral over gamma 2x ds, where gamma consists of the arc C1 of the parabola y is equal to x square from the point 0 0 to 1 1 as mentioned in the picture, followed by the line segment C2 from the point 1 1 to 1 2. So, right, first, so that means if I want to follow all the steps, then first I have to get what is called the parameterizations of the curve C1 and C2, and then I have to use the formula. But before that, since C1 union C2, so first I use the properties of my scalar line integral, that means integration over gamma 2x ds, which will be, what is this gamma? Gamma is at the C1 union C2. So, first you break up into two parts. So, one is integration over C1 2x ds and second one is integration C2 2x ds. Now, you have to calculate. Now, first one, what is C1? C1 is the parabola y is equal to x square. Starting point is 0 0 and end point is 1 1. So, first you have to get the parameterizations. So, what is the parameterizations of C1? So, C1 has a parameterization say R2, which is t comma t square, okay, and it is a joining point 0 0 to 1 1. So, that means t running from 0 to 1. You check it, this is the corresponding parameterization. So, then what is the corresponding integral here? So, if I calculate this scalar line integral, that means integration over C1 2x ds, what is this? This is 0 to 1, it will have 2 times, so 2 will come outside x. What is my x? This time is t, okay, and what is r? So, I have to do the r prime, right? What is r prime of t? This is nothing but 1 comma 2t, right, and you have to take the norm. So, that means if I do that one, that means what will happen? 1 plus 4t square and then dt. So, that is the integral you have to calculate, and if I do that, what will happen? So, this is nothing but 2 times. So, now just use the substitution. So, that means you assume that 1 plus 4 times t square is equal to s. So, that means what we will have? So, 8 t dt is equal to ds, okay. So, therefore, t dt is equal to, so 8 will come out 1 by 8. So, this should be something t dt, right, t times dt is ds. So, therefore, this is ds and then square root of s, right. But what will be the limit? So, now if t runs from 0, so that means s is from 1, and if t is 1, that means it should be 5. So, that means 2 by 8 1 to 5 square root of s ds. Calculate it. So, this should be 1 by 4, okay. Yeah, 1 by 4 integration 1 to 5 square root of s ds, and what is this? This is 1 by 4. So, calculate. So, then s to the power 3 by 2 divided by 3 by 2 1 to 5, s running from 1 to 5, that is the one. Na? What is this? 1 by 4, calculate it. So, 1 to 5. So, that means this should be 5 to the power 3 by 2 times 2 by 3 minus s is 1. So, I mean 2 by 3. What is this? So, that means 1 by 6 5 root 5 minus 1 by 6. So, that is the first one, this is integration. And what about the integration over C2? Now, what is the parameterization of C2? C2 parameter, C2 is just a straight line, right, with a starting point is 1 1 and end point is 1 2. So, therefore, if C2 has a parameterization, so let it be R2 del of t, and what is this? This is a starting point. So, that means it should be t times 1 comma 1 plus 1 minus t times 1 comma 2. You add it, what will happen? So, if I add it, the first one will give you 1, right, and second one will give you t, and then 2 minus 2t, that means 2 minus t, yes. So, first one is t plus 1 minus t, that means 1 will be there. Second one is t plus 2 minus 2t, t get cancelled. So, that means 2 minus 2. So, this is the parameterizations. So, that means what t running from where? 0 to 1. Okay. So, therefore, what is my integral C2? So, therefore, integration over C2 2x ds, which is same as 0 to 1, 2 times x. So, that means 2 times 2 will come outside, x is 1. So, 1, and then you have to have the derivative, right. So, what is the derivative of R2 del? Okay. So, you have to have the derivative. So, can write it as okay. So, r twiddle prime t, which is nothing but this is 0 and this is minus 1. So, what is the norm of r twiddle prime t? So, what is the norm of r twiddle prime t? So, this is nothing but 1, right. So, that means what we will have 2 times 1 times. So, 2 will come outside, this is 1 and this is 0 to 1 f of r t, that means 1, and then norm of r twiddle prime t dt. So, that means this is 1, right. So, what will give, this is the value will be actually 2, right, correct. So, 2 0 to 1 dt, that means this one will give you t, then is 1, then is 2. So, what is the value? So, you will have, so that means if I add it, that means you will have 1 by 6 5 root 5 minus 1 by 6 plus 2. What is this? This is 1 by 6 5 root 5, and if I add it, so that means it should be, yeah. So, 2 minus 1 by 6 na. So, that means plus 11, this is the one, and that is what it is, correct. 2 minus 1 by 6, so that means 11 by 2 minus 1 by 6, which is not by 6, 11 by 6. So, that means 1 by 6 take common, then 5 root 5 plus 11, yeah, that is the plan. Okay. So, that is why you can just use the properties of scalar line integral, break up and then get the parameterization each of the curve and then use the formula, that is it. Okay. So, there is a nice application is there of scalar line integral. What is that? So, suppose I am just writing one application. So, suppose you have a thin wire in the shape of a curve gamma parameterized by a smooth path, that means that the parameterizations of my curve gamma, it is r close interval a b to r t. Suppose it has the density rho x y, then the total mass of the wire is given by the scalar line integral of rho over gamma, capital gamma, and what is the center of the mass? This is x bar comma y bar. X bar is the formula 1 by m times scalar line integral. This time you have to integrand is changing, that means you have to hit it with x times rho x y, and y bar is what? 1 by m scalar line integral of y times rho x y. Okay. Suppose you have a thin wire in the shape of a curve gamma which has a parameterization small r and has the density say rho x y, then the total mass, this is the corresponding scalar line integral, and what is the center of the mass? This is x bar comma y bar, this is 1 by center of the mass times or 1 by total mass, this is 1 by total mass, then scalar line integral of x times rho x y, and this is 1 by total mass m, then scalar line integral of y times rho x y. So, once we know the notions of scalar line integral, then you can calculate this total mass and center of the mass. So, one examples I have given. Okay. So, this is the example. So, it says that suppose the wire W has the shapes gamma, gamma 1 plus gamma 2. You can also write gamma 1 union gamma 2, does not matter, where each parameterizations I have given, where gamma 1 has a parameterizations by small gamma 1 t, cosine t, sin t, t from close interval 0 to pi. That means actually I am talking about unit circle on the upper half plane. Okay. So, upper semicircle I am talking about. And what about gamma 2? Gamma 2 is parameterization by small gamma 2 of t. This is t comma 0, t running from minus 1 to 1. This y component is 0 and t running from minus 1 to 1. That means what? That means interval. So, you can easily calculate it. What is that? That means if I draw a picture, actually this is the one. So, gamma 1 means actually, so suppose this is 1, this is minus 1. So, that means, yeah. So, you have to start from what? 0, that means 1. So, this is actually gamma 1, and then you start from 1, come to minus 1 and then go in this direction. This is nothing but small gamma 2 and this is, okay. So, this is gamma 2, this is capital gamma 2. So, therefore, your gamma is nothing but gamma 1 union gamma 2. So, what is my curve? So, you have to start from here, go back here, then come back here. So, this is the gamma, capital gamma, which is capital gamma 1 union gamma 2, and each of the parameterization is given by small gamma 1 and small gamma 2. Okay. And suppose let the density function is given by rho x y is nothing but square root of x square plus y square. Then you have to calculate what is the total mass, what is the center of mass. Okay. So, first you observe that gamma prime t if I calculate whose norm is 1. Why? Because gamma 1, what is gamma 1 prime t? This is again minus sin t, cosine t. Okay. Now, if I take the gamma 1 prime t, then what will happen? This is square root of cos square t plus sin square t, that means this is actually 1. And what is gamma 2 prime t? Gamma 2 t is given. So, gamma 2 prime t, which is nothing but 1 comma 0, and if I take the gamma 2 prime t norm, this exactly equal to 1, square root of 1 square plus 0 square. So therefore this is perfectly all right. And what is rho of gamma 1t? Gamma 1t is given, rho is given, again this is square root of cos square t plus sin square t, that means it is 1. And what is rho of gamma 2t? This is nothing but square root of t square plus 0, that means it will give you mod t. Okay. So now I have everything. So norm of small gamma 1 prime t, gamma 2 prime t, rho of gamma 1 t and rho of gamma 2 t. You just calculate the total mass. So total mass, what is the formula? It is the scalar line integral of rho over gamma. Okay. Now since gamma is union of gamma 1 and gamma 2, you can just break the integral, integration over gamma 1, integration over gamma 2, integration over gamma 1, what it will give? It is the parameterization is given, small gamma 1 cosine t sin t, t running from 0 to pi. So therefore 0 to pi as it is. Then you have to have rho of gamma 1 t, so that means this is the constant function 1, then absolute of gamma 1 prime t, which is again 1, so that means this is 0 to pi dt, that is perfectly all right. And what about the second one? Second one over capital gamma 2, that means this is the parameterization small gamma 2, that means this is the integral minus 1 to 1 something, that means f of or rho of gamma 2 t, then gamma 2 prime t dt. Okay, now what is rho of gamma 2 t? That means this is nothing but modulus of t. What is gamma 2 prime norm? This is 1, so it will not contribute dt. So that means second one is modulus of t dt. If I calculate this one, what will happen? So that means you just break up into two parts. So that means first one, if t is minus 1 to 0, that means it is minus of minus 1 to 0 t dt, and second one if t is positive 0 to 1 dt. And you just do the integral, it will be pi plus 1. Very simple, right? So I mean this is break up into this one. If t is positive, that will give you 0 to 1 t dt, and if t is negative, one negative sign will come out, minus 1 to 0 t dt. You just calculate this integral, it will give you pi plus 1. So therefore mass, total mass I am getting. Now what is the center of the mass? Center of the mass is saying that this is x bar is 0, y bar is 2 by 1 plus pi. Again you can calculate what is x bar. If you calculate, x bar is 1 by m. So 1 by m means 1 by pi plus 1 as it is. Then integration over gamma. Then look at the formula. What is the formula? X rho xy, right? This time you have to hit it with by x rho xy ds. Again you calculate it. So this is 1 by pi plus 1 as it is. You break up into two parts, gamma 1, gamma 2. Gamma 1, if you just use the formula for the calculating how to calculate the scalar line integral, it is 0 to pi, and then x will be there. Now look, what is my x in this case? Cosine t. So this should be cosine t. Rho of x t gamma 1 t, this is 1. Gamma 1 prime t is 1, so that means this is dt. So that is the first one. Now if I want to integrate cosine t over 0 to pi, what it will give? It will give you 0. Nothing, it will not contribute anything, because cosine, what is the derivative of cosine? Is sine, and sine if I integrate from 0 to pi, it will not contribute anything. What about the second one? Second one is plus minus 1 to 1, x part will be there. Now in gamma 2, what is x? It's semi t, okay, and what is rho 2 of gamma t? This is mod t and then dt. Again you just break up into two parts. So what is this? This is same as minus will come out, minus 1 to 0 t square dt plus 0 to 1 t square dt, and if you evaluate it, this also give you 0. So therefore in that case x bar will be 0. Okay. And similarly what you can calculate y bar. Y bar if I calculate, so I do not have to any here, I can calculate what is y bar. 1 by pi plus 1, that is the total mass, again integration over gamma, this time what? Y times. So y times rho xy ds. Again you break up into two parts, gamma 1 and gamma 2. If I break it, so what it will give? So you just forget about this one. So that means first one is 0 to pi. Now look, so here y is replaced by, first I have to integrate over capital gamma 1. The corresponding parameterization is small gamma 1. That means this should be sin t, and then gamma 1 prime t norm, this is 1, that means dt. Okay. That means integration 0 to pi sin t dt, that it will give first one. And what about the second one? Second one is plus minus 1 to 1, then what will happen? Y times. Now what is my y? Y is 0. So therefore this is 0 times something, you don't care. So therefore that is always give you 0. What is this integration? If I calculate sin t from 0 to pi, that will give you 2. So that means the total integration y bar is 2 by pi plus 1, and that is exactly there, 2 by pi plus 1. And x bar is 0. So x bar, the first component is 0 as it is, and second one also is give you 0, because it is minus to 1 t times mod t dt. You just break up into two parts, minus 1 to 0, one minus sign will come out, that means integration minus 1 to 0 t square dt plus 0 to 1 t square dt. You just evaluate it, it will give you 0. So therefore x bar is 0, y bar is 2 by 1 plus pi. Okay. So, that is a very simple application. So, of scalar line integral. Once I have this formula, this is one of the very easy example. Okay. So, I think I should stop here. So, this is kind of very brief about scalar line integral. So, first I talked about what is the definition of scalar line integral, then I talked about couple of properties of scalar line integral, and then I give couple of examples I actually explicitly calculated, and then as an applications you can calculate the mass and what is called center of the mass. So, that is very brief about scalar line integral. In my next lecture I will talk about the notions of vector line integral. Again I will calculate couple of examples and some properties I will discuss in my next class. I think I should stop here. Thank you.